Hello guys, so today I would like to talk about oscillations. Let's start with the spring pendulum. So there are two types of oscillations I'm going to talk about, the spring pendulum and the string pendulum. So the spring pendulum is the simpler situation where you have an oscillation. So let's assume a fixed wall and a spring attached to it, attached to a mass with mass m, and the spring has a spring constant k. So now how can we express the force or the resultant force on the body or the mass m? So we know that from Hooke's law, we know that force equals negative k times x, where k is the spring constant and x is the extension. What else do we know about the force? From Newton's second law, we know that force equals mass times acceleration. And acceleration is the same as the second derivative of position. So now we have two expressions for the force and we can equate them. So negative k times x equals m times x double prime. Now let's solve for x double prime, or for the acceleration, by dividing by m. So x double prime equals negative k over m times x. Now we have, so our motion equations, which were these two, have led us to a differential equation. Now we would like to find a solution to this differential equation. So basically we have to find a function which is negatively proportional to its second derivative. And of course this is the sine or cosine function, so the sinusoidal function. I can show that by taking the general sine equation saying, or sine function saying y equals a times the sine of bx plus c. That means y prime, we multiply by the inner derivative, which is b times a times the cosine, sine becomes cosine, always remember that, of bx plus c, and then we take the derivative again, getting the second derivative, we multiply by the inner derivative again, which is b, so b squared times a times the cosine of bx plus c, and the sine. And remember the derivative of cosine is negative sine, we have to put a negative sign in front. And as we can see, something interesting happens. This part here is the same as this part here, which is the same as y. So let's insert that. Y double prime equals negative b squared times y. So this is an equation where the function y is negatively proportional to its second derivative. So that means that the sine function is the solution to this equation. So the sine function or the cosine function describes the motion of the oscillation of a spring. Now let's go on to the second case, the string pendulum. This is a little bit more complicated, but don't worry, you'll get it. So imagine a ceiling, a fixed ceiling, with a string attached to it, attached to a mass with mass m and length l. Now let's proceed by drawing the forces. Of course, we have the weight force and we have the tensioning force. Now let's decompose the weight force into a component which is parallel to the tensioning force, or to the string. So weight parallel and weight force perpendicular. Now, one thing I I should also introduce is that there is an angle phi here, which describes how much the spring pendulum has moved away from the equilibrium position. So what can we say about these forces? We know that weight equals mg. So because the angle phi is here and this vertical line is parallel to the weight force, phi will also appear here. And that means that the weight force parallel will be equal to the weight force times the cosine of phi. This is because the weight force, the parallel weight force is, if you imagine it to be like a, you can move the weight force perpendicular over here, and then this looks like a right angle triangle. And it is right angle because per definition we said that the weight force perpendicular is perpendicular to the parallel weight force. So this is like a right angle triangle with phi, and from trigonometry we know that the weight force parallel is the adjacent to the angle, so it will be the cosine. So therefore the weight force perpendicular, which you can see here, is opposite to the angle phi, and therefore we will have mg sine phi. Okay, and now what is the resultant force? We can see that the tensioning force and the weight force, they are equal and opposite, so they cancel each other out. If this wouldn't be true, the string would rip and the ball would go flying away, or the tensioning force of the string would pull the ball up into the ceiling. But in our case this doesn't happen, so they have to be equal and therefore cancel each other out. Therefore what we are left with is the perpendicular weight force. So that means the resultant force is mg sine phi. Okay, and now one thing I'm gonna have to say is that phi, hope this doesn't disturb any fellow mathematicians too much, but phi equals the sine of phi for very small angles, and we assume that these angles we're talking about here are very small. So we insert that, force equals mg phi. What else do we know about the force? Of course, from Newton's second law, we know that force equals mass times acceleration, which is equal to mass times the second derivative of position x. And now we can equate these two expressions for the force, giving us mg phi equals mx double prime. And this is nice, m cancels. But now we have a phi and an x double prime, so an x. And they are not the same. But we want to have an equation where we only have x's or only have phi's. And we know that phi times L is equal to x. Because if you assume to have a circle with an angle phi and an arc length of x, then the ratio of x to phi, or maybe better, phi to x, is the same as the whole circle 2 pi to the whole the circumference of the circle, which is 2 pi times, we call the radius L. This cancels, so we can take the turn them around, take the reciprocal, so we get x over phi equals L, or which also means that phi equals x over L. Yes, so that means that we substitute phi for x over L, g times x over L equals phi double prime, and this can be rewritten as phi double prime equals g over L times x. And so that we also have the negative sign, we can just assume that g is negative. Yeah, and now we have a differential equation as a solution again. And as we saw above, the solution to this differential equation is the sinusoidal function. So the sine and cosine function are what describe oscillations.